So when we graph periodic events, we recognize the cyclical nature of it. We've talked about some of these things. What is an example of something we looked at that had a periodic nature and could be represented with a sine wave? Good. The hours of daylight, right? Remember, we saw that that was a cyclical function. It changed over time. Tides also do this. There's a bunch of things that actually represent cyclical patterns. Also, we could talk about the radio waves like we just spoke about. What we want to be able to work on today is a little bit better understanding of how we can take data and turn it in to an equation from live coordinates. I just randomly threw these up here. What would be a reasonable X value for this? I don't know what the scale is, but what would you say an X value might be here? Seems kind of boring, doesn't it? Like 5, maybe? We'll make it easy. And then this one's a little bit away. Maybe this is 13. Okay. And now we need some heights here. And let's say that these are something like tides or something. So maybe this would be a 6-foot tide. And this would be 1. Get Miles's 1 in there. So in other words, this coordinate is at 5, 6. And this coordinate is at 13, 1. Believe it or not, if we know that this is a max point and this is a min point, we can create the full equation for sine with this. What's the general form of a sine equation? There's something in front. There's sine. There's something out front of the parentheses, theta, and there's something there and there. Does that look right? What does this thing refer to? Amplitude. What does this thing impact? It affects the period. It's usually called omega, and we know that the period is equal to 2 pi divided by omega. What's this thing? Good. The phase shift. And what's this? The vertical shift. Let's work our way back from the vertical shift this way. If we know this is the max value and this is the min value, what's the vertical shift? Five? I think it's like right here. Where is it relative to this 6 and this 1? Halfway between. So the midline is you take the y value of a max plus the y value of the min and divide by 2. You just take their average. So 6 plus 1 over 2, 7 over 2 is 3.5. So our midline is 3.5. So let's just put a plus 3.5 here. You guys with me so far? Can I, Ash, would you mind just lowering the lights a little bit? Okay, so we've got the midline already. We know that this runs right through the middle of 3.5. Already knowing the midline now, can we find the amplitude pretty easily? What's the amplitude? A little louder. 2.5. Good. How'd you get 2.5? So in other words, it's the y max minus the midline. The y value, max value, minus the midline. In this case, that would be 6 minus 3.5, which would be 2.5. So we'll put 2.5 as our amplitude. Okay, now, let's try to find the omega. Let's try to find the thing that affects the period. We know that when we look at a sine curve, normally it goes from a midpoint to a high, down to a midpoint, to a low, back up to a midpoint to complete a cycle. And I've often talked about breaking this up into how many parts? 4 parts. right? We say that we start here, we go to the end, we go to the half, we go to the quarters, and that gives us all of our coordinates. So if I'm looking at the max down to the min, what fractional part of a period is that? It's half, right? Each of these is a fourth. This is two of those fourths. So a max to a min is half of a full cycle. Well, how far is it from this max to this min? 8. So what would be our full period? 16. So let's memorialize this with formula here. If we were to take the we're finding the period. If we take the x value of a max minus the x value of a min, and these should be subsequent. Let's do like an absolute value there. That's going to give us how much of the period? Half. And so we'd want to multiply that by 2, and that's going to be the period. So 2 times 5 minus 13 absolute valued is -8, but it's positive, so 16. So the period is 16 is the period for this one. But does that mean we put a 16 here? No, because what we normally do is we say that the period is 2 pi divided by that thing that goes there, the omega. And in this case, we're saying that 16 is equal to 2 pi, and we don't know what that piece is. One of our properties of proportions is called the exchange property, which allows us just swap these two. You could do that out longhand if you wished. In other words, the omega here is pi over 8. This is our formula we've been using to this point. Turns out that omega is also equal to 2 pi divided by the period. So if you know the period, you take 2 pi divided by that. That'll find you this leading term in front of your argument to help you find the period. In this case, that would be pi over 8. How you guys feeling so far? 5, crazy, but I actually understand it. 3, I think I'm with you. 1, this is a good time for a nap. Sure. In order to find this piece here, we need to find what you would divide 2 pi by to give us the period. This time we know the period, though. Historically, what we've been doing is when we see something like it's, 2 in front of theta minus pi over 6 or something, whatever, we would take 2 pi divided by that 2, and we'd say the new period is that ratio, pi. Now we're doing it the other way. We're being given, effectively, the period is 16, and that's 2 pi divided by something. What I'm telling you is you can swap this ratio to say that the omega is equal to 2 pi divided by the period. In this case, we can say that omega is equal to 2 pi divided by 16, because that's our calculated period over here. Reduce that fraction to pi over 8. So pi over 8 is what we put in front of this now. Just 2 pi divided by the period. Now, this is the weirdest part. What is this? Phase shift. What does that mean? Left or right? Give me a little more. If we're doing the sine curve, this is where what part of the sine curve is moved to? The origin, like the 0, 0 spot, right? In other words, we need to find a spot on the curve that is this point, right? A midline point that's on its way up. That's the beginning of the sine curve. Do you see that? Signs like this, S, that's the beginning of it. So do we have that point here? Are we showing that point? We're not. But we do know that this is 8 units apart. And if I were to cut it up into fourths, what's halfway between 5 and 13? 5 plus 13 is 18, divided by 2 is 9. So this midpoint here would be 9, 4 units away from each. And when I go from a max at a 5 value for x, what would this one be as a midline? be 9, comma 2.5. 3.5, thank you. Right? Because it's our midline value. And then if I go another 4, which takes me to 13, I go down that same amplitude. 6 minus 2.5 gets me to here. 3.5 minus 2.5 gets me to here. And then what if I wanted to go one more this way? What would be my next coordinate? 17, comma 3.5. Excellent. You see that from the 13, we'd go over this same gap, this 1/4 of the function. And then we're coming back up to the midline, so it'd be 17, comma 3.5. What if I went to the left here? Right? This one's at 5. We've identified that if the whole length of this half period is 8, that means each of these quarter sections is 4. So if I go back 4, I'll be at 1. And it's at the midline here, so it'll be 1, 3.5. Now, I'm interested in finding my phase shift for the sine curve. Isn't this where my sine curve starts? You know what I mean by that? When we graph sine, we always start at 0, 0, go to the end of a period, go to 0. We produce this shape. That's a natural sine curve starting from the origin. It's a sideways S. The same is not true for a cosine. Where do we start a cosine? Up high. And then at the end of a cycle, we're back up high. Halfway in between, we're down in the low. And we end up with this cup-looking thing. So if we want to measure, if we want to call this equation, this graph that was given to us, if we want to give an equation to this that has sine as the descriptive function, we have to start it from here. This is where our phase shift has to be. If we wanted to, couldn't we create a cosine curve starting up here? Because that's a cosine curve. In this case, we're trying to do sine. What's our horizontal shift here? 1. So up here, we just put -1 because we're going to the right 1. And this is the function that describes the periodic curve containing this max and this min. Right? Good. Yeah, like 4-ish. I know it's going to take some work, but that's all right. Let's stick with this thread for a moment. Please go to page 3 of the packet I gave you. You'll notice that I've given you a sine curve here. This is just our normal sine curve. Starts at 0, 0, completes a cycle at 2 pi. Halfway through, it's 0 again at pi. Halfway there, it's at pi over 2, and it reaches a maximum of 1. Halfway here, it reaches a minimum of -1. And this is the cosine curve we talked about. I've also introduced the idea of a negative sign. When you put a negative out front of a function, what happens to it? It reflects over the x-axis. So this whole shape has reflected down. Instead of this being a max, it becomes a min. Instead of this being a min, it becomes a max. It also means that your amplitude now has a negative sign in front of it. And this is the way we work with amplitudes, right? We just take whatever we were supposed to be hitting, our maximum of 1, and multiply it by the amplitude. So if now we've got a -2 there, that's fine. We just multiply it by -2. So here's another example like the one we just did. This is point A. It's -17 pi over 4, comma 5. Each of these points represents a critical value. Here at 2, this is point B. Down here is point C. Back here is point D. Back up here is point E. This is point F. And we bottom out again down here at G. You guys with me? If I want to create the sine curve, just like we did, I'm going to say y equals, I'm going to have something sine, something theta, something, something. What would you like to find first? Take a moment, work with your neighbor, see if you can find both the amplitude and the midline. Find the amplitude and the midline. Go. All right, I'm hearing people saying the right answers. So who'd like to share with me what the midline is? What do you got? What's the midline? 2. How'd you know 2? BG and F are all at 2. That's one way to know. Does anybody have a different way to find it? Close. The distance between E and C divided by 2 gives me the amplitude. If I then subtracted that from the maximum, that would get there. Turns out you could also do it by taking the average of these two. Remember, the midline is the Y max plus the Y min divided by 2. But you're right. In this case, it's going to come out to be 2. What about the amplitude? Good. How'd you get 3? The midline? Good. Or you could take the Y max minus the Y min and divide by 2, right? Find out the whole big gap and cut it in half. That would be the amplitude. 3, okay. Now let's do the period. What is the period of this particular function, this graph? What does period mean? The length of time it takes to, louder, Grace, to complete one cycle. So I should go from what point to what point? C to G, that would work. Could we do A to E? Could we do B to F? Any of those would work. So let's go C to G. This one is at negative pi over 4. And this one is at 31 pi over 4. If I want to find the gap between them, do I add or subtract? I subtract. And in this case, that gives me a big negative number, negative 32 pi over 4. I really should have done absolute value. You might remember from your geometry days, the distance formula is A minus B absolute valued. So this makes absolute value of 32 pi over 4, which is 8 pi absolute value, so it's positive. 8 pi is the length of one period. Now, we also said that the period can be calculated as 2 pi divided by the omega, or the omega is 2 pi divided by the period. We want to find the omega so we can plug it into our equation. We found the period is 8 pi, so the omega is 2 pi divided by 8 pi, so 1/4. Who's with me? 5, I am right with you. 3, I can still see you. 1, where'd you go? Okay, good. The last piece is the most customizable piece, the most customly required piece, takes the most detail. Because we're doing a sine curve with a positive lead coefficient, which shape are we chasing after? Well, look at the ones above here. Are we chasing after this, 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 or this? 1, 2, 3, or 4? 1, because this is a positive sine curve. So we need to find the beginning of that S in our picture. What letter is the beginning of that S? D, right? And so this is my phase shift. I want to find out how far over it moves to get D from my center spot. We've already accounted for the vertical shift to here. So what's the X value of D? 7 pi fourths. So we'll just say negative 7 pi fourths, or minus 7 pi fourths. And that's done. This equation would now describe this entire curve. Yeah. Sure. The first step is to identify which curve you're looking for. Sine is this looking S thing. Cosine is like a cup because it starts at a max and ends at a max. Negative sine would be this flipped over the y-axis, the x-axis. So it's like an upside down one. And this is an upside down cosine. Since I'm trying to find the sine function here with a positive lead coefficient, I'm looking for this shape to be in my graph somewhere. That means I want to start from the left with this point, something that it's at the midline and working its way up. Well, this is not at the midline. This is at the midline, but it's working its way down. This is a minimum. This is the midline working its way up. So this is the start of a sine curve. If I had this shifted over just a little bit, it would look like my sine curve. So what I'm looking for is, what's the phase shift that gets me from my natural 0 over to d? Well, d has an x value of 7 pi over 4. So in other words, my shift is to the right, 7 pi over 4, or minus pi over 4, 7 pi over 4. What if I decided to do it with cosine instead? Same curve, but now I want to graph it in terms of cosine. Excuse me, I want to give the equation in terms of cosine. Does it change the amplitude? No. 3 cosine. Is the period going to change? No, it's the same graph, right? We're not changing the visual graph, so the period's not changing. It's 1/4. Is the midline going to change? Well, still the same function. All that's going to change is where we start. We can't start on D because that's the beginning of a sine curve. We're now doing a cosine curve. So we're going to start where? What's the start of the cosine curve? At a max. So like A or E, right? Either one of those would be a start. Let's choose A. So that says negative 17/4 pi. So I'm going to go positive 17 pi over 4 because it's moving. It's a negative, so we're going to turn it, positive. What if I want to do the opposite of sine? Does it still have an amplitude of 3? Does it still have a 1/4 impacting the period? Yeah. Does it still have a +2 to reference the midline? Because it's the negative sign, I'm going to put a negative in front of the 3 here. That's just forcing it to be a negative sign. And what point am I looking to start at? A, B, C, D? B. Good. This is the downward swoop of a sine curve. So all I have to do is look at B and say, what's my starting point? This is minus 9/4. So I'm going to say theta plus 9 pi fourths. Would you guys please do the negative cosine now yourselves? Go. So we know it's largely the same thing, right? Still cosine, still 1/4, still theta there, still +2. What do I put in front here? -3, good, because I want to force it to be a negative cosine. What point will I use? A, B, C, D, E, or F? C, because that's the bottom, the minimum, which is a reciprocal or the flipped cosine curve. C has a value of negative pi over 4, so I'm going to put plus pi over 4. We good? Okay. Tonight in your homework, you'll notice in the back, it's asking you to do that same kind of thing here. You don't have to follow exactly the pattern here. You can do however you want to do it. I'm not sure you're going to do the same way, but you'll notice that I'm only giving you the min and the max. So you'll have to work a little harder to find those other parts. The other piece for today is graphing tangent and cotangent. Do you remember when we started with cosine and sine? We started with a unit circle, and we said that the sine of theta is equal to the y value. And so we just found the y values, and we said, okay, well, this is the point 1, 0. So that means that the sine of 0 is equal to 0. So I know that the sine curve starts at 0, 0. And then we worked our way up to pi over 2, for instance, and saw that at pi over 2, it makes a value of 1 for y. At pi, it makes a value of 0. At 3 pi over 2, it makes a value of -1, and it comes back up. And this is how we created our sine curve, right? I want you to do the same idea with tangent. I want you to have a little sketch of a unit circle. And I want you to think about what the tangent would have to be. Now, I think I actually should have called this f of theta and tangent of theta to not mix you up, because cosine is x, and that's not the same as this x, right? Here we're talking about theta, which is the angle. But if sine is y value and cosine is x value, what's the tangent? Good. Tangent is y over x. So if I were to take negative pi, I come around over to here, there's negative pi. My coordinate is negative 1 comma 0. What would y over x be? 0 over negative 1, which is 0. Okay, please fill in these two columns now yourself. Go. Okay, great. I circulated around, saw a lot of good work. What I see is that at negative pi, it's 0 over negative 1, which is 0. When we get to the fourth coordinates, it's going to either be 1, because it's root 2 over 2 over root 2 over 2. Both negatives make a positive 1. Or when it's this one, we're down here, and we get a positive x, but a negative y, and so we end up with negative 1. When we're at negative pi over 2, that's down here. That coordinate is 0, negative 1, which means the y over x would be negative 1 over 0. What happens when you divide by 0? It's an undefined answer. We'll talk for a second about what that looks like. When I use 0, I'm back to the 1 comma 0, and that's going to give me 0 divided by 1, which is 0. When we apply the same rules over here, we end up getting the same results as we just got here. Now let's graph that. What this says is when I plot in a 0 on my x-axis, I'm at 0. No problem. When I go to pi over 4, I'm up at 1. When I go to pi over 2, it's undefined. How do I graph undefined? Good. It can never achieve this value. It's undefined. So I graph that like an asymptote. Then I look at 3 pi fourths. That's at negative 1. Pi is up at 0. That doesn't look helpful to me, does it? Well, let's try this part. 0 is 0. Negative pi over 4 is negative 1. Negative pi over 2 is undefined. Negative 3 pi over 4 is at positive 1. Negative pi is at 0. Well, I mean, I'm okay seeing these go together, but what happens over here? We worked on this with polynomials, didn't we? Graphing polynomials. If this is an asymptotic behavior, it's going to approach it. It's either going to approach it by going up or by going down. But if it went down, we would expect to see another what here? X-intercept. We'd have to have a different place where this function equals 0. That's not going to happen. So this is going to continue up, and this one's going to continue down. And we're going to see the same over here and the same over here. What did you notice about this data versus this data? Are they different? They're identical, aren't they? In the sine function, we have to go up to these positives and then come down to these negatives, and we finish it in a period of 2 pi. When we do the cosine function, what we're going to find is we get our 0 here, we get our 1 here, we get our undefined here, and then we get our negative 1, and then we get our 0 again. So has this cycled out in 2 pi when we do the ratio? Or have I seen every value between negative pi over 2 and pi over 2, and then it starts over again? Turns out that tangent has a period of just pi, not 2 pi. So now let's talk about how I like to graph these tangent functions. We know it starts at 0, 0, and we know that it has a period of pi. which means that if I split that period across both directions, pi over 2 this way and pi over 2 this way, I know that at pi over 4, I get a value of 1, and at negative pi over 4, I get a value of negative 1, and it has this positive slope-looking thing. If my period is pi, I can go from pi over 2 having an asymptote to 3 pi over 2 having an asymptote. In between those, I have a 0. In between this way, I have a negative 1. In between this way, I have a positive 1. And I get more swoops. From 3 pi over 2 to 5 pi over 2, again, I have a new asymptote. I have a 0. Would you describe this curve? I know it's not a straight line, but would you describe this curve as positive slope or negative slope? So in other words, the tangent has a positive slope, right? TAN, T looks like a plus. So this is the tangent curve. Let's go to page 2. And we're going to do some graphing with transformations, just like we did with the others. What does this 4 tell us? Good. Amplitude is 4. What does this 2 give us? It affects the period. The period is going to be whatever the real period was. It used to be 2 pi, but now we're saying that tangent has a period of pi over that. So now our period for this particular application is pi over 2. I'm telling you, when you start with tangent, there's no horizontal or phase shift. There is no vertical shift. So we start on 0, 0, just like we do with sine. But now I'm going to take that period and straddle the y-axis with it. If pi over 2 is cut in half, I'm going pi over 4 to the right and pi over 4 to the left. And tangent has a t to start, a positive. So I know that I've got 1s at my 45 degrees here that yield this nice positive sloping curve. And boy, that looks like a waste of space. So let's show more cycles. Again, if it's 1, 2 spaces to make the whole thing, I'll go 1, 2 spaces to make a new asymptote, 1, 2 spaces to make a new asymptote, 1, 2 spaces, 2 spaces. I'll even go negatives. 2 spaces, 2 spaces, 2 spaces. And halfway in between every pair of asymptotes, what am I going to have? A 0. In all these cases, I have zeros in there. And I know that halfway between the 0 and the asymptote is that 45-degree angle. The ratio is going to be a 1. Going to the left, it's going to be that 1 over negative 1 or negative 1 over 1. And I can just draw these in. Miles, yes. Oh, drat. Thank you. You're right. So you know how I did here to 1? I should have gone here to 4. Thank you, guys. My bad. The zeros are fine. The asymptotes are fine. I just should have gone 45 degrees up 4 and down 4. I tell you guys I bought a bunch of stock in erasers recently. Because I just made you guys all erase a whole bunch. Get it? Okay. Thank you for that correction. That's right. All right. 5, I can do that better than Mr. Erlin. 3, I can do it all right. I understand the pieces now. I just need to practice. 1, I'm unclear. Okay, good. Would you guys please go down and do number 2 yourselves now, please? Go. All right, let's take a look. So what's our amplitude? What's our amplitude? 6. Good. What's our period? Good. 2 pi. So I'm going to start. There's no vertical. There's no phase shift. So I'm quiet, please. Starting at 0, 0. I'm going to split in 2 directions. So I'm going pi to this side and pi to this side. At the halfway points, I'm going to go up all of the amplitude. So in this case, I'd go up 6. This case, I'd go down 6. There's my curve. I could do the same thing here. I notice that I'm going over 2 for each of the critical values. 2, 2, 2, 2. So if I go over 2, I'm going to be at a -6. If I go over 2 more, I'm at a 0. If I go over 2 more, I'm at a +6. I know that it's going to look something like that. How are we feeling? 5. I got this. 3. I'm getting this. 1. I don't got this. Okay. All right. Let's talk cotangent. We just did this. Go back to page 1, please. We did the tangent curve, right? And we did this last class. Hey, guys, please settle down. We did this last class in converting from the sine curve to the cosecant curve. How did we do that? Every place we had a 0, what did we turn it into? 1 over 0 is undefined, so we turn it into an asymptote. What happens at the value of 1? What's the reciprocal of 1? Still 1. Reciprocal of -1? Still -1. So what we end up with is these values are remaining the same. Somewhere in here, we've got a value of 1/2. If we did the reciprocal, we'd be up here at 2. And so we find that we get these curves. And this is the way we graph a cosecant curve, by graphing the sine and then reciprocaling all the y values. Let's do the same thing here. This spot has a y value of -1. What's the reciprocal of -1? Still -1. This spot is a 0. What's the reciprocal of 0? That's our asymptote. Just like we did with sine and cosecant. This is at a +1. What's the reciprocal of an asymptote? If the asymptote came about because we had 1 over 0, what's the reciprocal of that? 0 over 1, it becomes a 0. So we're trading our asymptotes for zeros, leaving our 1s and -1s the same, and trading our zeros for asymptotes. And the same idea we had with polygons here is I'm approaching my asymptote this way. I'm going to go up or down. I got to go up because I have no more x-intercepts. So do these shapes look a lot like the tangent? What are the 2 critical differences?
They're going.
Yeah, they're like negative slope. They go in the opposite direction. And they're shifted over. Instead of starting at 0 point like the tangent did, it starts with an asymptote off the 0 point. You guys know what an audible is? Besides a device that plays music for Amazon? It's when you're on a football field and the quarterback sees that something's awry, something's not working out, and he calls an audible. He changes the play on the line of scrimmage. Red 95, right? It's a blitz. So I'd like to call an audible right now. I think we need to practice cotangent rather than tangent. So please go to problem number 3 here, and let's change this to y equals 5 cotangent x. If you've jumped ahead and graphed tangent, I think it's really easy for you to then, use a different pen if you want, but it's actually good visual. Here, you want to?
That one, please.
All right. So what's our amplitude here? 5, good. What's our period? Pi, no change. And so when we start a cotangent, instead of starting at 0, what do we start with? What's the reciprocal of 0? Asymptote. So we're starting with an asymptote on the y-axis. And since the period is pi, let's go a whole period to pi and put another asymptote. That's the beginning of the next cycle. We can go up to 2 pi and do the beginning of the next cycle. Back to negative pi. Back to negative 2 pi. Now we know that halfway in between our asymptotes are what values? You may remember that in our tangent, halfway between our zeros were asymptotes, and halfway between our asymptotes were zeros. So what's halfway between these asymptotes? Zeros. Put in a little 0 halfway between each asymptote pair. And we know we're going to be dealing with like 1s and negative 1s. Is it a positive sloping thing or a negative sloping thing? Negative. So I'm going to come to this quarter point and go up, and to the right quarter point and go down. Thank you. I did it again, didn't I? Amplitude. So instead of going just up 1 and down 1, I'm going to go up 5 and down 5. So 5 is up there, but I still just have to make sure that I'm giving myself a negative slope for cotangent. What do you think? Easy peasy, lemon squeezy? All right. For your homework, would you please finish up this packet, which includes the back page doing some more curve fitting. And bottom of page 2, you're taking a graph and turning it into an equation. All right, that's your homework number 37.